All right, here goes video 2 for organometallic chemistry. So we talked about, a little bit last time about electron counting. We reviewed electron counting. We looked at a few fundamental steps. We're going to look at two different processes today. We're going to talk about alkene isomerization and hydroformylation. This is to remind you again, so we're talking about the topic of homogeneous catalysis. Those are transition metal complexes that are soluble, and common groups, and we've seen a lot of these already: metal hydrides, metal connected to carbon monoxide, metal connected to a phosphine ligand, metal connected to cyclopentadienide ligand, and metal connected to an alkene. Here again, I'm not going to spend a whole lot of time on this because we'll talk about these as we go through. All right, so here are some of the fundamental steps. So we start out with a reaction here. We have some metal complex and we react it with H2. And a good starting spot for a lot of these reactions is cleavage of H2. So this is an oxidative addition. Whatever the metal charge was here, it's increased by 2 units. H2, which was neutral, has now formed 2 hydride ligands. The complex now would somehow need to get an alkene associated. We had talked about earlier, it could be an associative or dissociative mechanism, doesn't really matter, but somehow we get a alkene coordinated, and it needs to be cis to one of these hydrides. After that, it undergoes an insertion reaction. At this point, if we did a final reductive elimination, we could eliminate an alkane, and we would have done a hydrogenation reaction. A really important industrial reaction is olefin isomerization or alkene isomerization. That's because our terminal alkenes, the ones that have the double bond in the very first position, are often more valuable in industry, and so these catalysts are important that will take an alkene and isomerize an internal double bond, one that's at the 2, 3, 4 deeper inside position, to a terminal alkene, the more valuable product. So we have this reaction here again. If we think back to where we were before, we start with an alkene bound next to a couple of hydrides. This is in equilibrium in most cases with the insertion product, where one of these hydrides has moved down and then has attacked one of the carbons of the alkene, and now we have a hydride and an alkyl attached. All right, this process that's here on the right-hand side is called beta hydride elimination. Let's see why that is. When we have a metal complex, whatever, for an alkyl, whatever carbon is attached directly to the metal is referred to as alpha carbon, and then from there, whatever is attached to the alpha carbon is a beta carbon. There could be more than one depending on how it's set up. But one of a hydrogen, or really a hydride, so this transfers as H minus to the metal center, giving us a hydride and now an alkene that's bound. So check out what can happen here. If I start here in the middle, I have an alkyl, and right here is a carbon, I have my highlighter on, and this carbon is alpha, but I have a beta carbon here, or I have a beta carbon over here. Each of those I can call a beta carbon. This beta carbon, if one of the hydrogens, so this is a CH3 group, if one of the hydrogens here migrates down to the metal, I'm left with a terminal alkene. However, if this beta carbon, which has a CH, has 2 CH bonds, if either of those migrates down to the metal, I'm left with an internal alkene. And so if this process is running back and forth, back and forth, back and forth in solution, I can isomerize from any pure alkene, either the internal to the terminal or the terminal to the internal, if I just let this process run long enough. All right, so the process would run something like this. I would start here with my catalyst. I might add a terminal alkene. I put it in. It undergoes a hydride. It undergoes an alkene insertion reaction. Then what happens is I have a choice once I'm at this hydride again, a hydride alkyl complex again. I could take either This is a beta carbon. This has 3 hydrogens on it. If I drop one of those down onto the metal, I would get back to my terminal alkene. If I drop instead this beta CH on, I'll get this internal alkene. And so I can start with the terminal and end up with the internal, or vice versa. All right, so this process, another direction that this can go is, if I start out with the alkene and I've got 2 hydrides on the metal, I can do an alkene insertion reaction, and then I can do a reductive elimination. And so overall, then I've created an alkane. Started out with an alkene and created an alkane in this process by doing an insertion followed by a reductive elimination. And now this is ready again to add more H2. So if we wanted to run this catalytically, we would add more H2. We would make the dihydride. We would add more alkene and H2. We would end up with this complex, and we would run it. We would do the insertion and then reductive elimination. And now this is a catalyst again, so we keep regenerating this guy. We add more H2, and we add more alkene. We get up here, and we can run that around and around and around. The second important type that we're going to talk about is olefin or alkene hydroformylation. Another really important industrial reaction, 6 million tons per year a few years ago when I put the slide together. I take an alkene and H2 and CO, and I get aldehydes out of this. Again, it ends up being that the aldehyde product is more valuable than the, well, this would be not an aldehyde, but a ketone product. So this aldehyde product is more valuable than the ketone product that could come out. There's a bunch of different catalysts that can do that reaction. So how could we start that? So again, we've got a system that's got 2 hydrides, it's got an alkene attached, it's in equilibrium with this insertion product that has a hydride and an alkyl. What we'd shown before, we can have this go and do a reductive elimination, and up here at the top, we've just taken the alkene and we've hydrogenated it. But what could happen if we had a CO that's in there? Back in the last lecture, we talked about those CO insertion reactions. And if we take this guy right here, which is a hydride and an alkyl, if I can get CO to bind to that complex and do an insertion, I now have a hydride acyl. This hydride acyl can do a reductive elimination and give my metal back and give me an aldehyde product out. This would be ready to grab again hydrogen and an alkene and form this sort of species, undergo the insertion, then we're back down here, hit it with CO again, do CO insertion, and then have the aldehyde be released again. Here's that shown in a cycle. So I start out with this complex here, add H2, do an oxidative addition, add alkene to give me my alkene dihydride complex, do an alkene insertion in order to give me my hydride alkyl complex, add CO, do an insertion reaction. Now I have a hydride acyl complex, do a reductive elimination to release the aldehyde, and now I'm back to my starting material again. It can accept H2, accept an alkene, we get back to this species and just run the cycle over and over again. All right, so it was found that this cobalt hydride complex can catalyze isomerization of pure cis-2-butene to a mixture of cis-2-butene, trans-2-butene, and 1-butene. I'd like for you to propose a mechanism for this. Carefully show the process using wedges and dashes to indicate the stereochemistry of each of the intermediates. This will be due Monday, March 23rd at noon. Again, you can write this on paper and scan it. You can take a snapshot with your phone and send it to me. You also, there are some apps I know for the iPhone that you can make a PDF directly by snapping the photos and make a PDF. That would be the best if you can do that, but any of those I can work with. Be coming to you with another video again pretty soon.